Okay, so passive filters. Passive filters, I'll do the other audio ones properly tomorrow. But passive filters, so no power. I need to remind you of the reactance of a capacitor. So if we were to model a capacitor as a resistor, it could have some resistance. So we use the formula 1 over 2 pi Fc. So it's only modeling it. And how does that look on a graph? Well, the reactance of a capacitor goes down as you go up in frequency. So we can use that formula. If we use a 200 nanofarad capacitor there at 100 hertz, popping into there has a reactance of 7.96. So it could look like a 7.96 kilo ohm resistor. Now, some questions ask you to then work out the reactance capacitors at other frequencies. Now, if they go up in a factor of 10, like we are here, we don't need to recalculate it, because if we go up in a factor of 10, then actually the reactance of the capacitor would go down in a factor of 10. So it'd go down to 796 and then 79.6 as we went to 10 kilohertz. The reason why we do that is because then we can use that in a filter design, which is effectively a potential divider, because we can model this capacitor here and here as effectively a resistor, so it's got reactance. Now we've got these two passive filters, a treble cut and a base cut. How do I remember it? Well, this capacitor comes before the resistor on this one, so this is the easiest one to remember. So base cut comes before. This one, the capacitor comes after treble cut. It's far easier when you look when we talk about the active filters for this one, but try and remember this one. But the capacitor comes before, so that's the base cut. Okay, so we've got these two filters, so therefore then we can actually then come up with some designs. Now remember, they will only have a gain of maximum of 1, so the maximum you can ever get out is what you put in. Anything else is going to be less. Okay, so how does it work out then? Because we don't actually have a resistor, so we just remind you of the potential divider formula, which is this V out across R2, so R2 divided by R1 plus R2 times V in. Now it depends on what we've got here, but in the example that I'm going to, sorry, not got onto that yet. So when we then look to then take the combination of resistance and capacitance, doesn't matter which one we've got, then what we actually cover, when we've got combination of resistance and capacitance, the resultant that we get is called impedance, Z, which is R squared plus XC squared. Okay, so that's the combination of R and XC. So if we look at this example, then I've got my capacitor here, so that's across my output. So first of all, we'll want to work out what the break frequency is. The break frequency is when XC equals to R. So when the value of that equals that, so we can pop that into the formula and we get 3.18 kilohertz. Okay. Right. So if we then look to say, well, what our bandwidth of our filter is going to be, well, if we've got 10 volts coming in, then at our break frequency, we have got 70% of that maximum, which is 7 volts approximately. Okay, so that's what we got, and we can plot that on a graph. Now, it's quite often that we might want in a numerical calculation to work out what the voltage is going to be at another frequency. Well, as this capacitor is after, this is a treble cut circuit, so before this break frequency, we're going to have a gain of approximately 1, so it would make sense to look at what the output is above this frequency. So if we look at it, what it's going to be at 4 kilohertz, then we need to work out what the reactance of the capacitor is at 4 kilohertz. Okay, and then we can pop that into our impedance calculation to work out what the impedance the circuit is going to be. So the combination of resistance and reactance. Okay, so we've got that value, we've got the reactance, the capacitor, and we've got the combination of our reactance and resistance called impedance. So we can now pop them to use them two together to work out what our output is going to be. So as this is a treble cut circuit with V out across there, so we're going to use the reactance to start with, reactance to the capacitor, and then that is going to be divided by, which would normally be as a potential divided question, R1 plus R2. Well, our R1 plus R2 is our reactance of our capacitor, okay, and then multiplied by 10 volts. So above that break frequency, our output is dropping off now, as we would expect it to do. Drawing a frequency response graph for these passive filters, we need to be able to draw two types of frequency response graphs. First of all, a log. So let me talk you through it. Well, we're going to put a line in at whatever our voltage, our maximum voltage is, or whatever our or if we're just talking about gain, that would be 1, and then we would then put a point in at our resonant frequency, like so. And then, because this is a 2-point approximation, what you can see in red, we would draw a 45-degree line coming down, like so. Now I've just gone slightly better with that, and I've actually put in a point at 70%, so I can then draw this green line in like that. But certainly the red line would be that would get you the marks. Okay, so you've got the red line, which is 2-line approximation, or the more accurate version, which is in green there. There is only one solution for drawing it on a log linear graph. So the logarithmic part still goes in the frequency, the linear goes up here on the side. So we're starting off at our maximum output at our break frequency, so at 3.2 kilohertz, and we know that the maximum output is approximately 7 volts. So we're going to put a point in there, and then we're going to start to draw a curved line that comes down from the maximum down through that point at the break frequency, and then we need to curve it off as it comes down to the 0 volts. Okay, so it curves off as it comes down to the 0, okay, on a log linear graph. Marvelous.